Alrighty, so there are two more types of Newton's laws problems that I'd like to go over before we get to friction. Once we hit friction, basically it's going to be reviewing all of Newton's law problems, all the different types of problems we've done, but allowing friction to be involved as well. So these are the last two different type of Newton's law problems, that is, problems which involve forces. So let me start with elevators. What's an elevator style of problem? The main problem is this. Let's say we have an elevator. Here it is. And there's a person in the elevator. And they're standing on a weight scale. Okay? So they're standing on a weight scale. Let's say the mass of the person is 100 kilograms. Just to have a nice round number. And so you can ask, what is the weight of the person? That is to say, what does the weight scale say that they weigh? He's sitting there, or she is sitting there, standing. I'm going to say he, because 100 kilograms is kind of heavy. This person is standing on the weight scale. Let's assume the elevator is not moving. It's just standing there on whatever level. And so obviously, if the elevator is not moving, then you don't really know it's an elevator. It's just a room. And you're standing on a weight scale. What would the weight scale say? Well, we know weight is just a fancy type of force. It's a very specific force that we call weight, but it's really a force. And we know F equals ma. That's what Newton's second law says. But what's special about this F equals ma for weight is that the A involved, the acceleration which causes the weight, is gravity. So that ma is really m times g, where g is the acceleration because of gravity. So all of this is to say, when we want to calculate the weight of an object, it's m times g. We get it from F equals ma. F equals ma is the big equation that says whatever force you're talking about gives rise to the mass of the object times its acceleration. If that acceleration is gravity, then that force is a special force that's called the weight. That's all I'm saying. So if we want to calculate the weight, we take the mass of the object multiplied by g, 9.8. So for this person who's just standing there, 100 times 9.8 tells us the weight of this person is 980 newtons. Okay. Well, so far we haven't done anything with the elevator. This is just, can we calculate the weight of a person? If we know the mass of the person, we multiply by 9.8. That gives us his weight. That's what we've done. Now, we will incorporate the elevator's motion. So let's say part A. Find the apparent weight of the person if the elevator rises with constant velocity of 5 meters per second. Okay. So what's the situation? Here you are. You're in an elevator by yourself. You're standing on a weight scale. You push the button to go to the second floor. The elevator moves. As it's moving with a constant velocity of 5 meters per second, you would like to find out, how heavy do you feel? What is the apparent weight? That is, what will the weight scale say your weight is? Okay, all three of those terms or statements are the same. Your apparent weight means how heavy do you feel Not how heavy are you, but how heavy do you feel because of your motion. And it's also the same as saying, if you were standing on a weight scale, what would the weight scale say your weight is? It may be different than your real weight. That's why we call it apparent weight. It might not be your true weight. And of course, we know, if you're in an elevator and the elevator's moving, sometimes you feel heavier than normal. It's like you're being pushed into the ground. Sometimes you feel lighter than normal. Maybe it feels like you're being raised up again off the floor. So, here's a question. The elevator's rising. If the elevator rises with a constant velocity of 5, moving upwards, what do you think the weight scale would say? Well, first, let's forget about doing the math. Let's use our intuition. What do we think? Well, we're in an elevator. We've all been in an elevator, I'm sure. As the elevator rises, how do you feel? Do you think you feel heavier or do you think you feel lighter? Well, for me, my own personal view, when the elevator starts to move up, I feel heavier. It's almost like I feel like I'm being pushed into the ground. But that's at the beginning. That's when the elevator first starts to move. But let's say we're in a very, very tall building. When we first start to move, it's like I get pushed into the ground. But then, as the elevator continues to rise, I don't feel that way anymore. I kind of feel normal. In fact, if I wasn't looking at the little window that tells me what floor we're on and we're rising up number by number, I wouldn't actually be able to tell that I'm moving in an elevator. So, if that's the case, if I'm not talking about the very beginning when I first start to move, but I'm talking about the time in between as I'm rising in the air, if I can't tell that I'm moving unless I look at the numbers or I hear the little dings as each floor goes by, then I would assume my weight wouldn't change. But let's see. Let's do the math. What does the math say? The math says my weight is the same as saying my force. And I know my force is equal to MA. Okay? So when I want to find my apparent weight, it's the same as saying what's the force on me. Let's do this. Let's do a very fancy way. If I want to say what are all the forces acting on me? So let's do the sum of all the forces. What are all the forces acting on the person in the elevator? Let me draw it on the picture. Obviously, gravity is pulling down. That's mg. Gravity is always pulling down on us. However, I happen to know I'm not falling down through the ground. If I'm not falling down through the ground, that means the ground must be pushing up, preventing me from falling. So there must be some other force pushing up on me from the ground. That force I call the normal force. I'm not going to go into the details about the normal force for now. That's going to be held for friction. But for now, just realize that the normal force must exist because I'm not falling. I'm not going through the ground. I'm not falling through the weight scale. I'm being held there, standing there on a solid ground. Even though gravity is trying to pull me down, if I'm not actually going down, that means the floor must be holding me up with a force. I call that normal force, just to give it a name. So if those are my two forces acting on me, then the sum of the forces is minus mg. That's gravity pulling me down. Then there's a normal force pushing me up, preventing me from falling from the ground. So those are the two forces acting. Let's look at the right side of this equation. The right side of the equation says ma. Well, the m, that's my mass. Okay, that's fine. What about the acceleration? What acceleration am I going? Look at the problem. The problem says Find the apparent weight if the elevator rises with constant velocity of 5. So what's the acceleration? Well, the problem says specifically I'm moving at constant velocity. Whatever the velocity is doesn't matter. The fact that it's constant means my velocity is not changing. It's 5 and it stays 5. Well, acceleration is a change in the velocity. So if I have no change in my velocity, then my acceleration must be 0. So that's easy. In this specific instance, if I'm not moving with an acceleration, I'm moving with a constant velocity, then my acceleration must be 0. So there it is. So here's my equation. Minus mg plus normal force is equal to 0. Solve this, and here's the key. Anytime I'm looking for apparent weight, that means calculate normal force. Okay. Another word for normal force is apparent weight. How heavy do you feel? What would a weight scale say your weight is? All of those things mean calculate normal force. So here's my equation. Minus mg plus n equals 0. Solve it for n. Bring the mg to the other side. N equals mg. Plug in my numbers. M is 100. G is 9.8. So I get 980. What does that mean? When the elevator is moving at a constant velocity, whether it moves up or it moves down doesn't matter. If it's moving at constant velocity, I'm not accelerating. If I'm not accelerating, my acceleration is 0. Solving for normal force, the normal force is equal to mg. Mg is my actual weight, the true weight of the person. So in this case, for part A, find the apparent weight for this particular instance. It's the same as my true weight, 980 newtons. The same as if I wasn't moving at all. And that matches my intuition. My intuition was, forget about when the elevator first starts to move. But if I'm in a 20-story building and I'm moving up, there's floor 6, floor 7, floor 8, and I'm just moving up. If I don't look at the numbers, I don't really feel the fact that I'm moving. It feels like I'm just standing in a room. And if you covered your ears and you weren't listening and you closed your eyes, you would have no idea you're in an elevator. So you should feel as if you weigh the same as your real weight. And that's what this says. Mathematically speaking, the normal force, which is your apparent weight, what the weight scale should say, is the same as your true weight. You don't feel heavier and you don't feel lighter. Even though the elevator is moving, if it's moving at constant velocity, your apparent weight should not change. But, of course, that's only one type of instance. We could also have an instance where a person is standing on a weight scale. And let's say for part B, what is your apparent weight if the elevator rises with an acceleration of 5 meters per second squared. Okay, so very similar problem, except in this case, we're not told it's moving at constant velocity of 5. It's actually accelerating with 5 upwards. It's rising. Again, let's look at our forces. mg pointing down, always. That's gravity. The fact that I'm not moving through the floor tells me the floor is pushing back with a normal force, n. So let's now use F equals ma. The sum of all the forces acting on me is equal to ma. What are all my forces? mg pointing down, so minus mg. My normal force is pointing up. Those are all the vertical forces in this problem. What about the right side? The right side says m times a. All right, let's plug my numbers in. Minus mg plus normal force up equals 100 is my mass. What's my acceleration for this problem? This problem says my elevator rises, so it's positive, with an acceleration of 5. So positive 5. So what do I have? Minus mg plus normal force up is equal to 500. What do I want to do? I'm trying to calculate my apparent weight. Apparent weight means calculate normal force. So I want to solve this for n. Bring the mg over to the other side. What do I get? Normal force equals 500 plus mg. Well, of course, mg, that's 100 times 9.8. So I have my normal force, my apparent weight, the thing I'm searching for, is 500 plus 980. That's 1480. What does this say? This says the weight scale would say I weigh 1480 newtons. What's my true weight? My true weight is only 980. Does this match my intuition? My intuition would say, okay, I'm accelerating up. That's the same as when, like, the elevator first starts to rise. At the very beginning, you push the floor. It first starts to rise. When you first start to rise, the elevator is accelerating upwards. It feels like I get pushed into the ground. So it's almost like I feel heavier than I really am. I'm being forced down harder than gravity alone. So my intuition would tell me if the elevator is accelerating up, I should feel heavier. The mathematics says my true weight is only 980. Here I calculate my apparent weight to be 1480. That is bigger, so it works. It matches my intuition. I expect a heavier weight. I calculated a heavier weight. What about part C? Part C is almost identical, only this time find the apparent weight. If the elevator falls with an acceleration of 5 meters per second squared. Okay, so very similar, only this time, instead of rising up, I'm falling down with this acceleration. So we do the same thing. There's my picture. I already know what all the forces are. So sum of the forces equals ma. What are all my forces? Minus mg down, and normal force is pushing me up. There are my forces. The right side, well, the mass, that's still 100. What's my acceleration now? Well, now my acceleration is still 5, but this time I'm falling. I'm moving downwards, so it's negative. So my acceleration is negative 5. So minus mg plus normal force up is negative 500. What am I looking for? I'm looking for the apparent weight. That means calculate the normal force. So bring the mg to the other side. Normal force is equal to mg minus 500. All right, plug my numbers in. 100 times 9.8 minus 500. What does this say? This says my apparent weight is my true weight, mg, minus a certain amount. I should feel lighter. In fact, 980 minus 400 is 480 newtons. Does this match what I would assume by logic the answer should be? Well, imagine you're in an elevator and the elevator starts to drop. Right at the beginning, as soon as it starts to drop, in my mind, I picture myself rising off the ground. So it feels like I'm being lighter than I really am. So I would assume the weight scale would think I don't weigh as much as my true weight. Here, mathematically, my true weight is 980. The math says my apparent weight is only 480. So indeed, this matches. My apparent weight is less than my true weight because the elevator is moving downwards with an acceleration. If it was moving downwards with a constant velocity, of course, the acceleration would be 0, and there'd be no difference. My true weight and my apparent weight are the same. This is how you calculate an elevator problem. They're all identical. What are all the forces? Weight pulling down, mg, normal force pushing up. The only difference is what do you put on the right side? And that depends on the situation. Are you accelerating or are you moving at constant velocity? If you're moving at constant velocity, then ma is just 0. If you're accelerating, then of course you need to know, are you moving up or are you moving down? Up is a positive acceleration, down is a negative acceleration. So if you're accelerating upwards in an elevator, then you should feel heavier. Your normal force should be bigger than your weight. And of course, if you're falling with an acceleration, you should feel lighter. And so your normal force should be less than your weight. Those are elevators problems. What about pulleys? Let's look at a pulley problem. Here's a nice one. Here's a pulley. One side is a block. Here's another side with a different block. Let's say this block has a mass of 5 and this block has a mass of 10. They're connected by a rope over a pulley. I'm holding on to the system and then I'll let go. What's going to happen? Let's consider that before I ask the question. When I let go of the two blocks, what do we expect will happen? Well, it seems to me the left block weighing more than the right block, the left block should fall down and the right block should rise up. So my assumption would be this guy would move downwards and this guy would move upwards. Here's the question. Find the acceleration of the system and the tension in the rope. So obviously I let go, the two blocks start to move because one is heavier than the other, and they're going to accelerate. And I'd like to know, how do they accelerate? Obviously one will accelerate down and the other will accelerate up, but the actual number for the acceleration will be the same for both because they move at the same time. The other thing I want to know is what's the tension in the rope? The last video we discussed said tension just means how much force runs through my rope. Okay. How do I go about solving a pulley style of problem? No matter what problem you have, if it involves pulleys, you're going to go about this the same way. So take note of this. There's two pieces of my system. I've got two different blocks. Block of 5 kilograms and block of 10 kilograms. Okay? Let's call this guy, the block of 5 kilograms, block 1. And the other guy, block 2. Since I have two different blocks, I need two different equations. Each block will have its own equation. So let's look at block 1. Block 1. Here he is. Let's look at him. Here he is. He's got a mass of 5. What are all the forces acting on this guy? Well, obviously, gravity pulls down on him, so there's some mg pulling down. Let's call it m1 times g, because it's block 1. Are there any other forces? Well, sure. There's a rope which connects block 1 to block 2. And I already know by my own intuition that block 2 is going to pull downwards, which is making block 1 go upwards. So that rope pulls on block 1, applying a tension, because the force is through the rope, so we call it tension. So there's some force upwards, and we call it T, capital T for tension. And those are the only two forces which act on block 1. His weight is pulling him down, and the rope is trying to pull him up. All right, now all we have to do is F equals ma for this particular block. What are all the forces? Minus m1g, pulling him down. Tension is trying to pull him up, so he's positive. There are his forces. Now we look at the right side. His m is m1. What's his acceleration? Well, I don't know A, but is he upwards or is he downwards? That is, I can look at the system and I can tell, will block 1 move down or will he move up? Since block 1 weighs less than block 2 will move down and block 1 will move up. That means block 1 has an upwards acceleration, which means he has a positive acceleration. So, positive A. Whatever the A is, I don't know what A is yet. I'm trying to find it. But I know he's positive. So there we go. There's my equation. What can we do? I'm looking for tension and I'm looking for A. Can I solve this problem? Think about that. I want to know the tension, and I also want to know the acceleration. And there's my equation. Can I get both answers? Well, if you were to ask me, I would say no. Unfortunately, we cannot solve this problem because here's a single equation that has two different unknowns. I don't know T, and I also don't know A. But I only have one equation to try to use. So this is not solvable yet. This is why we need a second equation, which will be block 2 later on. But for now, all we could do is choose one of the letters, one of the variables, to solve for. I could either choose T or I could choose A. It doesn't matter which one I choose. Let me go ahead and choose T because it'll be easier. So I'm going to take this equation and solve it for T. In order to do it, of course, I bring m1g to the other side. So I add it to the other side, and I have T equals m1a plus m1g. Okay, so all I did was get T by itself. But that's as far as I can go because I don't know A. I don't know what this number is right here. If I knew it, I could get an answer, but I don't know it yet. So let's leave him alone. Let's look at the other block, block 2. What does he look like? Here's the block, 10 kilograms. What are all the forces acting on block 2? Well, of course, he's got his own weight, so there's some m2 times g pulling down. And of course, the rope is connected to him, and that block 1 is still trying to pull downwards, which would pull up on block 2. Even though he's not heavy enough to do it, he's still pulling. So there's still some tension trying to stop block 2 from moving. And the rule is, if you have a single rope, then the tension is the same everywhere. What that means is the tension on block 1 has to be the same as the tension on block 2 because it's the same rope. You can't have one part of a rope feel more force than another part. The whole rope feels the same force everywhere on it. So this T on block 2 is the same T as block 1. That's why I don't have to call it T1 and T2 or something like that. It's just T. But Again, there's block 2. There are all his forces. The weight is pulling him down. The rope is trying to pull him up. Even though he may not actually rise up, it's still trying to do it. All right. F equals ma. What are all the forces? Well, I've got minus m2 times g trying to move him down. And I've got tension trying to move him up. Those are his forces. Right side of the equation, m2, that's his mass. What about his acceleration? Well, I already considered this. Block 2 is heavier than block 1, so block 2 will fall. Block 2 will move downwards, thus his acceleration should be negative. So minus a. Okay, block 1 will rise, so he's got a positive. Block 2 will fall, so he's got a negative. Can I solve block 2? Well, no. Again, I still can't solve block 2 because block 2 still has 2 unknowns. T is unknown and A is unknown. However, notice now I have 2 equations. Here's one equation, here's a second equation. I know if I have 2 unknowns, I could solve it if I have at least 2 equations, and now I do. So now, if you remember the algebra review we did at the beginning of the semester, we went over how to solve 2 equations with 2 unknowns. The way we did it was substitution. Take one of the equations, solve it for one of the unknowns. I just did it. That's what this one here is. I took my first equation, solved it for t. Once I have it, I take that t and I plug it into my other equation for his t. So now what do I have? Minus m2 times g plus t, but t I just solved for. That's m1 times a plus m1 times g from my block 1 equation. So minus m2 times g plus t, but t is this whole thing, equals minus m2 times a. Now look at this equation. Is this equation solvable? Well, ask yourself, how many unknowns are in this equation? Do I know what m2 is? Yes, m2 is 10 kilograms. Do I know what g is? Of course, g is 9.8. Do I know what m1 is? Yeah, m1 is 5 kilograms. Do I know what a is? No, a is unknown. But that's the only unknown in this equation. So here I have a single equation with only one unknown in it. This is a solvable problem. Take this equation, solve it for a. Well, of course, one thing I could do is plug numbers in. Minus m2, that's 10, times 9.8, plus m1, that's 5, times a, plus 5 times 9.8, equals minus 10 times a. So you can see, I've got a whole bunch of numbers with a. Solve this for a. Well, let's see. Let me bring 5a over to the other side. That'll make this right side negative 15 times a. But what is the left side? Minus 10 times 9.8, that's 98. 5 times 9.8, that's 49. So, what do I have? I've got a equals 98 plus 49. Sorry, minus 98 plus 49 over negative 15. So what will my answer be? I get 3.27 as my acceleration. But that's only one of my answers. I've now calculated A. That's good, but I still need to find T. So how do I get T? Well, now that I have A, look back up here. plug this a right here into that a there, and I can calculate t. So what do we have? T equals m1, which is 5, times a, 3.27, plus m1, which is 5, times 9.8. So, what do we get? 3.27 plus 9.8, all of that times 5. I get T is 65.35 newtons. And there we go. A nice, normal pulley problem. So let's look back how we solve a pulley problem. You're given two objects connected by a rope. That rope goes over a pulley. You let go of the objects, and the pulley starts to move. In this case, looking at the blocks, block 2 is heavier than block 1, so block 2 is going to move down, which makes block 1 move up. Okay. How do we solve a pulley problem? Well, we have two different objects, block 1 and block 2, so we're going to need two different equations. Let's look at block 1 first. Block 1, look at block 1 here. There's the 5 kilogram block. What are all the forces? mg is pointing down, and the rope is trying to pull him up. So minus mg down and t pulling up. Do F equals ma on block 1. What are all the forces? Minus m1g plus tension up. Those are the forces. Right side of the equation, the mass is m1. A, I don't know what A is, but I leave it as A. But I happen to know that block 1 is going to move upwards because block 2 is heavier. So since I know block 1 will move up, I make this A positive A. Unfortunately, I can't solve this equation because there's two unknowns. I don't know T and I don't know A, so I leave it alone. Look at the second block, block 2. Here is block 2 right here. Block 2 has two forces, his mass times gravity, pulling him down, and the rope trying to lift up on him. And now I do F equals ma for block 2. What are all the forces? M2 times G is pointing down, so minus M2 times G. And the tension is pulling up, so plus T up. Those are all of his forces. What about the right side, MA? Well, M2 times his A, and again, I don't know what A is. However, I do know M2 is the heavier guy, so he will be moving downwards. Since he moves down, I make his A negative A. And again, two unknowns sitting in this equation. Again, I don't know T and I don't know A. Once this is done, all of the physics of the problem is over with. All of this stuff over here and this stuff over here, all of this is algebra. Two equations with two unknowns. So what I did was I took the first equation and solved it for t. That's what I did over here, right here. Solve for t, so t equals blah, blah, blah. I took that t and I plugged it in right here to the second equation for his t. And that gave me this stuff right here. From that point, the only thing left in that equation is a bunch of a's. So I do my algebra, get all the a's on one side, all the numbers on the other side, and I solve for a. In this case, I got a to be 3.27. All right, so now I know his acceleration. The acceleration of the system is 3.27. That's one of my answers. I still need to find t. So I say, okay, well, now that I know a, go back to my first equation. That equation says t is blah, blah, blah with an a in it. So I now plug my a into that guy, and I can calculate what t was. So that's what this thing is here. Plug the a into that equation, and now I have an equation for t with a whole bunch of numbers. Plug all the numbers in, calculate it out, and I have a tension. Every pulley problem you do will be just like this. Some pulley problems, I will warn you, will be like this, where you have a block up here with a pulley and a block down here. How would you go about solving this? Same way. Call him block 1, call him block 2. Block 1 will have M1G, pulling down, tension, pulling up. What would block 2 have? Well, block 2, his M2G is downwards, but I know block 2 is not going to move down. Block 2 is going to move left and right. His tension, here's the rope right here, so his tension is trying to pull him to the right. So for 1, I have F equals MA. All of those forces are Y forces. M1G is pulling down, tension is pulling up, those are Y forces. When I do block 2, F equals MA, what's the direction of block 2's motion? Left and right. In fact, to the right. He'll be pulled to the right. So I only need to look at the X forces for block 2. I don't care about Y stuff for block 2. Block 2 is not going to move up and down. So when I do his F equals MA, his F is tension to the right, and that's it. We don't have to worry about his weight. We don't worry about M2 times G, because M2 times G is a Y force. But the motion of block 2 is an X motion. So since his motion is in the X direction, I only want X forces. That'll be the difference between this problem and this problem. Here, everything was up and down, so all the forces were Y forces. Over here, one of the blocks is up and down, so he's a Y thing, but the other block is left and right, so he's an X thing. However, other than that, you solve this the same way. Block 1 will have a T and an A in it, so 2 unknowns. Block 2 will have a T and an A in it, 2 unknowns. So again, you're going to have 2 equations with 2 unknowns. The equations might look a little different than the other example we just did, but the principle is the same. I've given you the key concept difference, which is block 2, you have to look at the X component stuff only. So I feel you should be able to figure out how to solve this problem. If you can do this previous example, this one here, and you truly understand what you did, then look at this example. Can you solve this? You should be able to. Block 1, F equals MA for him. Look at all the Y forces. Block 2, F equals MA for him, but you only look at the X forces. 2 equations, 2 unknowns. Take one of the equations, solve it for T. Now that you have him, plug him into the other guy, and then you have an equation for A. Solve that equation for A, you have one of your answers. Now that you have that A, plug it back into the first, and now you have T. Exactly the same as this previous example. All right, so I think that's good enough. We now see how to solve these 2 styles of problems. We've got the elevator, where there's basically 3 different systems. The elevator can be moving with constant velocity, in which case the normal force or the apparent weight is the same as the true weight. The elevator can be moving upwards with an acceleration, or it can be moving downwards with an acceleration. And for each case, you should be able to calculate what is the apparent weight. What that means is calculate normal force. When you're rising with an acceleration, you should feel heavier. When you're falling, you should feel lighter. If you're moving at a constant velocity, you don't feel any difference than your normal true weight because you're not accelerating. The other, of course, are the pulley problems. You're either going to have a pulley like this where they're both moving up and down, or you're going to have a pulley like this where they're moving left and right. Of course, you could also have a pulley that's on an inclined plane like this. And you should be able to do this as well. Here, this guy is moving in the parallel direction, so F equals ma will be parallel forces. And of course, you've got mg as a y force, so you'd need to do this kind of a thing. But block 1 will have mg down and tension up. They're all the same. Two pieces of your system, two F equals MAs, one for each block. Which direction will the block move? If it's in the y direction, then you need F equals MA in the y direction. If the block moves left and right, then you need F equals MA in the x direction. Blah, blah, blah. Once you have the F equals MA set down, then at the end of the day, you have two equations with two unknowns. You do the normal algebra stuff to find the T, the tension, and the A, acceleration. If you can handle this system, then you can handle these two systems as well. They're the same thing. All right, so I hope this was helpful and got you going, and you now understand how to do this style of problems. The next will be friction. So that means we're going to go back to the beginning of Newton's laws, a block sitting on a nice flat horizontal table. You apply some forces to the block, but now there's going to be friction. How do we incorporate friction to F equals MA? That's what you can look forward to next. Once that's done, test time will be coming up, so we'll be having an exam review. And so we'll get, a nice look back at all the things we've done so we can be prepared for this first test. So until then, I hope you understand what's going on.